Well, good evening, everyone, and thanks for joining us for another Our Universe Revealed, which is the public lecture series from the Department of Physics at the University of Notre Dame. My name is Jonathan Crass, and I am the series coordinator. I'd like to extend a warm welcome to all of you this evening and say thank you all very much for joining us. If you want to know more about our upcoming events, please do visit our website, nduniverse.org, where you can also sign up to our mailing list. You can find us on Facebook and on YouTube as well. The format of our event this evening is going to be our usual setup from the past few talks, with a presentation followed by questions at the end. You can submit those questions at any time during the presentation, so if things do come to mind during the talk, feel free to send those questions in, either via the Q&A button at the bottom of your Zoom window if you're connected that way, the chat window on the right-hand side of your screen if you're watching in YouTube, or I'll send out shortly a Google form link that you can also submit questions through if you'd prefer to do it that way. Tonight, it's my pleasure to welcome Professor Alejandro Clocchiatti to Our Universe Revealed. Alejandro is a visiting professor in the Department of Physics at Notre Dame and a professor in astronomy and astrophysics at the Instituto de Astrofísica at the Pontificia Universidad Católica de Chile. His research focuses on the study of supernovae, which are violent explosions of massive stars, which are caused by those stars running out of nuclear fuel at the end of their lives, which powers them. Tonight, however, he's going to talk about a broader topic and one of the fundamental principles of science, and that is how science has the ability to make predictions based on evidence and data. So welcome, Alejandro. Thank you very much for offering to speak to us this evening. And let's see, hopefully, if we can get your screen sharing working so everyone can see your screen.
Okay, thank you very much, Jonathan. Let's see, do you see it?
That looks good to me.
Okay, so everything ready? Shall I get started?
Go ahead.
So I extend my thanks. Thank you very much, all of you, to be there listening. I will try to walk you through an interesting path of discovery and understanding of the world that started many years ago. I proposed a title to the organizers of this talk, but fortunately they didn't pay attention to me, and you will see why in a few more minutes. So the backdrop of the talk is going to be this idea of a flat Earth. And I recommend an article, this one that is going to be there. And I am using that picture to show one more, way in which the people that believes, and I emphasize believes in this, imagine the Earth is just a flat disk floating in the sky with the moon, sun, and planets moving around up there. And well, the plan of the talk is rather reality and us, looking at it from the point of view of a scientist. And the title complete would have been like that: flashes of a history of ideas about the world, the intellectual tools that we use to understand, a pinch of how they were threaded over time, some of the riches of their application to our everyday life, followed by some musings about the dangers of forgetting what we used to know. As you see, that is not a very catchy title, so I am glad the organizers thought of something else. Regarding the subjects, I will touch some part of the archaic thinking, Anaximander and Pythagoras, classic thinking, Plato and Aristotle, fast forward to the late Renaissance, Kepler, Galileo, Descartes. Actually, my goal is to reach Newton, the apple. I am sure that most of you have heard something about that story, but I would like us to reach there with the context to understand the meaning, the momentous of that thought of Newton at that time. Then I will follow with some nice things about the interpretation of the world in terms of the Newton ideas and physics. And then we'll go down to some more recent subjects like understanding the coronavirus infection and some very little about the physics of climate change. So let's move on with this part of the talk. And it could start like a tale, like those that you tell children when they are going to sleep. Once upon a time, there was a people who began to try to understand the world without making reference to gods, just looking for natural laws. We have to go back to the Greek archaic period to find the first natural philosophers. They were born and grew in the city-states of Greece around the Ionian area. Miletus was the first place where Thales of Miletus, the first philosopher in the Western tradition, is recognized to have lived. Then we will mention Athens because a couple of important ones were there, Croton in the southern part of Italy, and Alexandria, that was a very long-lived Greek colony in what is now Egypt. Anaximander was a student collaborator of Thales of Miletus, and he, together with a friend of him that had traveled a lot, Hecateus, came up with the first map of the world that has sort of a modern flavor, and this is 6th century before Christ. Anaximander regarded Earth, the top part of it, as a flat cylinder, and he added that the thickness was 1/3 of the diameter. Also, that the Earth is poised alone, aloft, supported by nothing, and remains in place because it is equidistant from any other thing and thus has no disposition to move. Well, Miletus is there, suspiciously close to the center of that disk, and you would ask Anaximander why he thought of a cylinder. And it is a common theme in this early history that natural philosophers tend to look for similarities between the geometrical shapes and those things that were out there in the world. The same here. This is sort of a physics principle. Since it is equidistant, it doesn't move. So I will remind Steven Weinberg in one of the books that I am recommending, how do you know? He says that after reading these manuscripts from these guys, that's a question that comes to mind. How would you be so sure that things are like that? Well, let's move forward like a couple of centuries to Athens. And there we have Aristotle, young Aristotle, starting to systematize the world and the knowledge about the world. He was speak in terms of guidelines of things that a natural philosopher should follow that later on became known as doctrines. And Aristotle could very well become dogmatic, or at least the followers dogmatic. So he said that natural laws must follow from first principles, reason, logical reasoning, and common sense, but this is interesting, must save the phenomena. So if natural laws do not reproduce what you see, then they are not good. Doctrine 2, there is an underlying backbone of reality that can be expressed in terms of math and geometry. This can be traced back to Pythagoras, that was in between Anaximander and them. Pythagoras has one of the first hits of natural philosophy, I would say. He discovered what is now called acoustic. He found the mathematical principles under sound, and that was important because it revealed a tendency of nature that you can express the laws of nature using math and geometry. Plato made more of it by imagining that everything we see around here is not really what it is, but the real part of it, the reality, is behind, cannot be grasped by the senses, but it has to be understood by the mind. So if you see a cone like a pine tree, it is just a reflection of an ideal form, and natural philosophers will use capital letter for that form, which lives in this ideal part of the universe that we can reach only with our mind and not with our senses. So these basic two principles guided much of the systematizing of Aristotle, and he applied that to the shape of Earth. Is it spherical? He paid close attention to the shape of Earth's shadow on the moon during lunar eclipses. It is pretty clear that the lunar eclipses are a situation where the Earth comes in between the moon and the sun. And if you pay attention to the shape of the shadow, you see that if you want to reproduce that shape, this is the same picture with different exposure times. So it is clear in this one. If you try to reproduce that shape with anything else that is not a sphere, especially if you pay attention to the fact that you see that shape, if the eclipse is on the zenith, right on top of your head, on the horizon, on anywhere in between, then you are pretty sure convinced that the Earth has to be spherical. And that is probably one of the few things nice that I would say about Aristotle today, one of the few compliments, and one of the few things that I am going to say about geometry of Earth, Moon, and Sun. Because I am more interested in the other dimension of this, the Aristotelian physics and what brought it in the later times. Aristotle had an idea, again from Plato, that there were four natural elements, earth, water, air, and fire, that they had the natural places on this world, and the natural motion resulted from the natural places of those things. And then the concept of violent motions, that is when you move one thing out of the natural place and that thing tries to go back to the natural place. On top of that, he built an Aristotelian cosmology that was earth-centered with the prescription that motions had to be circular with constant orbital speed. Those are motions of the planets outside of the Earth, and gave rise to the duality earth-heaven, and the heaven was made of a fifth element, quintessence. This dichotomy is also known as the lunar-sublunar dichotomy. But let's go back to the question of Steven Weinberg. How do you know? Okay, natural motion is like when a ripe apple falls from a tree. It tries to go to the natural place because it is made of water and earth, which is heavier than air. So moves towards the center of Earth because everything which is heavy follows that path. And violent motion is if you grab that apple and pitch it far away, then as long as the apple is in your hand, it is moving with violent motion. And as long as you release the apple, it should try to go back to the center of Earth, which was the natural tendency of things that are heavy. So the observation showed that it didn't happen. So that gave rise to a host of possible explanations answering the question, what keeps an object in motion if the natural tendency should be to go back to the center of Earth? And that question was tried to be answered in different silly ways along many centuries. So let's view this in a timeline scheme. These axes here are years, 500 years before Christ. This is Christ, 500 years after, 1000, first millennium, 1500. We have some interesting names in there. This is from a course of history of science. I'm not going to speak about all of these guys. We have just mentioned these ones. But this timeline represents very different worlds as the years and centuries went by. These guys in here were pre-Socratic. These two that we have mentioned were Hellenic. That's the classical period of Greece. These ones were after Alexander the Great, and they work in the kingdoms that resulted from the splitting of his empire. And then came the Roman Empire, and things started to go back. These guys in here were doing great science by the time. Please read the book of Lucio Russo. It's a very interesting time of human history. Roman Empire was not good to this initiatives, they had a good decades, 2 decades, 50 years or so, which is called the Pax Romana. In that time, Ptolemy appeared. We should be grateful for that, because in this period, many of the things that transpired to the rest of the history were put together. Things started to go worse a few centuries after that. We had the splitting of the Roman Empire, collapse of the western side, the destruction of the Alexandrian library, where most of the people had been working, and the followers of them. Fortunately, along this long 1,000 years, we had the Byzantine Empire, and that was good for keeping the ancient wisdom preserved for the future. Many good things happened in the north of Africa and Europe, but from time to time only. Among them, the Arab expansion, which was great. Arabs got in love with Aristotle and copied and studied their manuscripts, and they were preserved then for the future. The Carolingian Empire, the nascent Europe, was starting to show their might. And finally, the Renaissance. And in the Renaissance, two very important people. Copernicus, I'm not going to talk about him. He moved the Earth out of the center and put the sun in there. Tycho, you probably don't know much about him, was the greatest observer in history before the invention of the telescope. And among them, they prepared the world of science, or proto-science, for the Renaissance. This was the most luminous part of history, probably, I don't know if humankind, but certainly of Europe. And what I am going to ask you to please not to get scared or freak away, because I'm going to show a few equations, very simple. But in order to understand the meaning of what Newton thought when he saw the apple falling, we need to have a little grasp at these equations. Please do not freeze. These are like children encrypting code for a game. So I will use two codes just. One is the equal sign, like in A equals B. And it means whatever you have on the left side equals whatever you have on the right side. And that's what equation means, two things that are equal. And the other symbol is that one, means A and B, like in here, are proportional. If one grows by a percentage, the other will grow by the same percentage, or decrease, or etc. So let's move to Kepler, Galileo, and Descartes, which lived pretty much within the same time, in the same time. This was a time when Aristotle and Plato were finally left behind. And I would like this to show this nice picture by Raffaello with Aristotle the younger, and Plato pointing up to the world of ideas and the forms. Aristotle thinking, well, professor, maybe we should go down earth a little more. And there we are, Descartes, Galileo, and Kepler. Kepler provided us with an exquisite, I would say, quantitative description of the motion of planets. After studying for, well, 10 years about observations that Tycho had done for about 30 years, he found that the planets do not move in a circle like Aristotle sustained, but in an ellipse. The sun is in a focus and the planet gets closer and farther, closer and farther. Also, that as it does so, it gets faster when it is closer to the sun and moves slower away when it is farther away. It's like if the planet is falling, goes back, then falls, goes fast, and like that. And finally, the third law, almost exactly 400 years ago, after 20 years of working with Tycho's data, and is the farther away a planet is from the sun, the slower it moves, in such a way that the period, so is the time it takes to take a circle, is proportional to the distance, that distance cubed. So this is the first time in many, many centuries that a person after Pythagoras came up with this nice mathematical representation of something in nature. Regarding Galileo, most of us know Galileo because of his clash with the church and the telescopic observations. But what I would like to bring here is rather his work on physics. And he was actually interested in proving that the Galilean doctrines regarding the motion of bodies were wrong. So he did study a lot the falling bodies. How do they fall? Aristotle sustained that heavier bodies fall faster than lighter bodies. We will never know for sure if Galileo really dropped balls from the Tower of Pisa, but maybe so. There are no records. What is true is that he was paying serious attention to it. He was able to prove that bodies of different weights will fall with the same speed. That was against the doctrine of Aristotle. And also, very interesting, that those that start with a horizontal velocity will fall following a parabolic path. This is one of the machines that he would use to demonstrate that. He will drop a ball from here, and the ball will start this motion and fall following this path. What is a parabol? Well, these distances in here, these ones, are proportional to those distances squared. If we call this x and this y, this is it. Y proportional to x squared, or y equals kx squared. Also, after he was condemned to be in prison after the clash with the church, he spent a lot of time looking how bodies fell. This is one of his devices. He will drop a ball from up there, and the ball will tick along these devices, finally dropping here. And he was able to demonstrate how to increase the velocity of the ball. But in particular, if he connected this part in here of the device with a horizontal path, he will notice that the body will not stop. So he was able to come up with the first expression of what we now know as the principle of inertia. He realized that the old Aristotelian question is not what keeps an object in violent motion moving, but he turned it around. The question is why an object that is moving at a given speed would change the speed at all. So, isolated from the rest of the world, left to itself, an object will keep on moving with the same speed forever. This is the first time that someone came with the principle of inertia. This is another view of these machines in a different museum. Let's go to Descartes. Descartes is also known as a philosopher, and I would like to bring in here something different. He was the person that invented the Cartesian coordinate system, and it's like this device. He was inspired by the maps that were very popular at his time. You can put points in here and, I don't know, solve a game or send a code to a friend, a drawing, or you can invent something that we call a variable, and it's something that you move in here, like x, and connects with another one in here through a function. In this case, a proportionality. I mean, you increase this and you increase that in the same way. You can also draw Kepler's ellipses there, or Galileo parabola in there. You will recognize Galileo parabola if you do that. That branch of the parabola is what Galileo had found with his machine. So nerdish, sleek, elegant. This is something very good for doing geometry and math. Also, he came up with the final version of the principle of inertia. Isolated from the rest of the world, left to itself, an object in motion will keep on moving with the same speed and direction. Finally, you know, it is interesting. You show this picture in any country, any age of the kids or young people, and you ask, who is him? And they will say, Isaac Newton, everywhere. So, Newtonian physics, please stay on. It's your chance to learn Newtonian physics in just 3 slides. So, Newton was pretty convinced, because of the work of the previous people, that why an object keeps moving is just the boring part of physics. He could draw this on the Cartesian diagram, coordinate system, and say, okay, if this is time, this is x, then the object will move just like that, increasing the position as time goes by. X is proportional to t. I could come up here and pick up a time, t1, see that at that time the object was at position x1, pick up a second time in there, see that the object was at that position, then take this interval. This is the difference in time. Let's use this capital D, and take that interval in there, the difference in position, and compute that. dx over dt, this is the velocity, the average velocity between times t1 and t2. And this is as much as I can do. If I do this math an eternity before t1 or an eternity after t1, I will get the same number. But look at this. In that case, the velocity is changing all the time, not only in direction, but also in speed. I know that because of the Kepler's law. So the interesting thing, the fun part, will be why and how an object changes its position and follows such a well-defined and beautiful geometric curve. How do you tame, how do you deal with a variable velocity? Let's go back to this plot. This is the constant velocity case. But if the velocity is variable, in here, the object is moving fast, it starts fast, gets to 1 yard in less than half a second, but then it takes more than half a second to reach the second yard, and then it has stopped and start going back, decreasing in yards the position. So if you go and do the same trick, take the x1 and t1, take the x2 and t2, compute the difference in time and in x, you compute the velocity, average velocity, and you know that that's going to be different. E here is fast, E here is slower, and E here it has stopped. So how do you deal with a variable velocity with these tools? If you are like me, I would go back to the apple tree and rest. But Newton was Newton, so he invented a mathematical process that allowed him to take this t2 time and approach it infinitely close to t1. He made that into that. So a difference into a differential. Newton invented differential calculus. We are not going to teach that in this talk, but that allowed Newton to move from the position in yards to the velocity in yards per second, for example, back and forth. Time and x in here, time and velocity there. So he would know the differential change in position at any time, and he would know the differential change in velocity at any time. And that is what interested him. Why? Because this is acceleration. And for any arbitrary motion, then he was able to go back and forth between velocity and acceleration. What took him many years of ingenuity and work now takes us like 2 semesters in college. So Newton could go back from A to X. And why was this fixated? What is fixation? Well, because Newton had one hunch and one certainty. The secret keys of the universe were encrypted in Kepler's law, position and velocity. And the key to understand this was the acceleration, how the velocity changed. And how do you change the velocity of a moving body? You use a force. So Newton came up with that idea. The velocity, the changes in velocity are proportional to the force. That's Newton's idea. Didn't have to be like that. So what is the proportionality? Well, he thought of a mass. If someone throws at you a can of Coke, you have to do a force to stop it. If someone drops at you, 2 cans of Coke, you will have to do twice much as a force, 2 times as much the force. So if you divide the force by the mass, you get the same change. If you made the mass triple, then the force will be triple to stop that. So you move the mass to the other side of the little equation and you get this, and you know that this is the acceleration. So you start to notice that, and that is F equals ma, the famous equation that Newton came up with. So now Newton has converted this into this, from x and velocity, position and velocity, through acceleration to the force. And that is when finally we can understand the meaning of the day of the apple. When Newton saw the apple falling to the tree and the moon in the back, he said, could it be that the same force that makes the apple fall from the tree is the same force that makes the moon rotate around the earth instead of keeping on moving as it should if it was alone in space? So he tried with that shape for the force, a force that is proportional to the mass of Earth and the distance between the Earth and the moon. And his equation, he discovered that he needed one more equation. This is the principle of action and reaction. And with all of those equations, he was able to, using differential calculus, move from his hypothesis, his laws of movement and the force, to Kepler's law. So he could check his thoughts. Newtonian physics was born certified. Humanity had gotten physics. The principles of natural philosophy, the Principia, were published on July the 5th, 1687. And I think that that's the day when modernity was born. In that book, there is a nice explanation of tides, things that had been known to sailors for millennia. No one understood how to explain them. Newton explained those things. Neap tides, when the sun and moon are in quadrature, and spring tides when they are aligned. In the flat Earth model, you cannot explain tides. Another thing that you can explain with Newtonian physics are eclipses. And I would like to show this because they are beautiful. These computations have been done by Fred Spenak, and you can go to the NASA pages and find this sort of map. And any eclipse, you can take a plane or a train or a car and go there, and you will see this happening. I know that because last year I was in Chile and I watched from Santiago this eclipse, July the 2nd. I saw it partially because I was outside the cone of shadow of Earth. This is the shadow, different path that the moon will do in the different eclipses at different dates. So this one was very important here. 2017, August 21st in the United States. Many of you here in the States should have seen it. I saw this one in Chile, July the 2nd, 2019. And a friend of mine was just in Coquimbo and took this picture. And you see nicely aligned Earth here where we are, the moon and the sun. But getting that, that alignment with the equation and knowing in which place of Earth this shadow is going to fall each second of time is marvelous. If you want to understand this a little, in more human terms, think of these models of the solar system that I am proposing here. If the sun was a sphere of diameter 1 yard or 1 meter, depending if you prefer the imperial or metric system, the sun-Earth distance will be like 107.5 yards or meters, and the Earth diameter will be 1/3 of an inch in imperial system, or 9 millimeters. The moon will be 10 inches closer to the sun than the Earth, or 25.5 centimeters in this model, and the diameter will be 1/10 of an inch. And using Newton equations, you can predict the motion of these three things which are moving and exactly where the shadow of the moon is going to fall on the Earth at each given time. So in the flat Earth model, you cannot predict eclipses. And if the Earth was not spherical and will not follow the Newton's law, you will not be able to predict these eclipses as good as they are predicted. So let's speak a little about this, which I call the 19th century power guys. Michael Faraday, James Maxwell, and Hendrik Lorentz. What these people do? Well, they provided most of empirical, starting with Faraday, and theoretical, starting with these two, basis to understand the motion of charged particles under electromagnetic force. So they understood electricity, basically. They did what Newton had done for the gravitational force. Instead of putting in here gravitation, they put this force, which is much more complicated. I'm not going to speak about that, but I'm going to show you an example. If you have a magnet, like a horseshoe magnet with the North Pole and the South Pole, and you have a current in there, like a cable with a current, then the cable will feel a force directly in this way. So it's pretty complicated. But let's have a look at this short video. You will not hear the noise, but there you have the captions. Just 1 minute, because it's very interesting to see these forces as they are.
Alejandro?
This will be a simple motor in which you have an armature here, the stator, which is a magnetic field, the armature is the current, and when you connect a battery in here, like this, then you will see
when the current flows through the coil, an electromagnetic force is induced on it according to the
you will see
law. So
a motion, a force appears. This is Lorentz force, and you will make
connect with the power source of opposite polarity.
Alejandro, I think we're still just seeing your PowerPoint slides, not the actual video in YouTube.
Sorry?
I think we're just seeing your PowerPoint slide. We can't see
Oh,
the video.
sorry. Okay. So cool. Please go and watch this video. Excuse me. I was not sharing the right screen at this time. I apologize. Please have a look at this video. It's just a very simple explanation of how this force is used to move a motor, an electric motor. The interesting part of it is that an electric motor is also a generator. If you put a battery, you get movement. And if you move the motor with your hand or with a, I don't know, an axle, then you will get electricity. This is a picture of one dam, the Columbia River Grand Coulee Dam. And if you pay attention to that, in that place, you have these devices which are moved by the water falling. You have a turbine in there and the generator in here. And these are enormous things. The turbine is this thing that you have in here, is being brought down with the crane, and the generator is even larger and goes on top of this. And what I wanted to point out is that the physics then that explains the power generation is the same physics, the same series of mathematical descriptions of reality in Newton's laws with the electromagnetic force now, the same physics that explains Kepler's law, the tides, the eclipses, and the street lights, the keyboards of the computers we are using, the screens, the optic fiber of internet, and this conference. If physics didn't work, then you will not be watching me. I will not be here talking to you. And that same physics explains why the Earth is approximately spherical. So Earth cannot be flat because I wouldn't be here talking to you. So time has passed by. This is another timeline where we have Anaximander and Pythagoras back in here. This is the ancient Greek chronology, not our years, but the years that the ancient Greece, people in Greece was using since the first Olympic game. And you see clearly that about 2,250 years had passed between these people and Newton, and about 2,600 years from Anaximander to us, with 378 years of physics. So you cannot pretend now that these things have not happened. You cannot hide Newtonian physics and math under the rug and pretend to go back to discuss the shape of the Earth as these people here were doing. Time has passed by, and we should be paying closer attention to reality. We cannot afford the luxury of not paying attention to it. Why? Well, let's go back to this. And I will show you a toy model. As long as Newton and motion, to explain the change of velocity, you need a force. How do you explain the change in infected people when you are in a pandemic and every one of us is susceptible of getting the sickness? So the infected people, the increase in infected people should be proportional to the infected people. If one of us is going around infected and we infect in average, I don't know, 2 people, that's one thing. But if 10 of us are going around infected, then we will infect 20 people among us. And if, well, 10 times that will be 10 times more. So you have this proportionality. And the funny thing is that it is even easier to get the constant of proportionality here. Why? You just answer, how many people does each patient infect and how long is he or she contagious? And that's the constant. Number of infections over the time that you are infectious. We know with coronavirus from the time of infection in China, the pandemic in China, that each patient infected 2, 3, 4 people in that about 10 times they were infectious. So that's the equation. And everyone that knows calculus knows that the solution of that is that thing in there, is exponential. And y is the initial number of infected people. But the critical part of it is this. That implies the doubling time of 2.3 days for that toy model. But let us see what happened in a real case, the increase of infections in the United States. Well, if you follow the trend of the first 33 days, you get that number, doubling time 2.4 days, which is pretty much the same as the one that this very simple toy model that will make any I know epidemiologist get mad at me, but this very simple model will reproduce that first part of increase. A few more days later, it is slightly different, but still very short, doubling times like 3 days. This means that you have 10 infected people today. In 3 days more, you will have 20, and in 3 more, you will have 40, and in 3 more, 80, and in 3 more, 160, and so on. So if you are a politician and your epidemiologist come here, you are the prime minister or the king or the president, and tells, sir, we are in deep trouble because the infection is starting to show in here, but you see this around and you cannot believe what's going to happen. But you should rather pay attention to your epidemiologist, to your scientist, because they know this model and the more elaborated models, and they know that in 3, 4, 5 more weeks, you are going to be counting the infections by hundreds of thousands of people. So in the United States, things almost, well, got out of hand in many places. In some other countries, same, France, Italy, Spain, Russia now. But it didn't need to be like that. Look at the Koreans did, South Koreans? Well, they got it great, sharp increase early on, and then they were able to keep it down there. So if I had a decision, power of decision, I will give the keys of the world to the Koreans and ask them to drive. So we cannot afford the luxury of not paying attention to science. Between these and these, there are thousands of people that have gotten sick and many that have died. So finally, physics and climate change. In the 19th century, there was a different breed of physicists that developed a different kind of physics that applied to ensembles of particles, a gas, liquids, and this is thermodynamics, statistical mechanics, radiative transfer, later quantum mechanics and the study of light, and those got some of the greatest hits of physics. They allow to predict radiation, heat, how those things interact, and masses of gases and liquids flow. So it is tough physics, but you can do it. Our colleagues that do climate science use this all the time, and since the late 19th century up to now, they have been growing models in complexity, each time more precise and more elaborated. And we are finally, like past 10 years, this stage where we can model our world, the atmosphere and seas and land of our world, the oceans, with the ice, the vegetation, the dust flowing in the wind, etc. They do that by building a grid, little cells of air and land in which they consider every physical process that takes place there: advection, movement of air, transfer of water, air between the ocean and the atmosphere, water coming, snow coming and flowing back into the sea, radiation coming and going. And each little square is made even tinier as computers develop more and more. So you gain resolution, and you gain resolution also in the vertical direction by making these little squares each time smaller and smaller, and considering all the physics that goes in between, even the inputs that we do to that physics, like the emission of gas from our industries and cars. So what do these guys get? In this plot, it is increase of temperature as time goes by in comparison with the level that the temperature was in the 70s and early 80s. And we see that the models, which are these thick lines in here, follow the observations, which are these colored lines in here, pretty well. I mean, there is some uncertainty, some things that they cannot reproduce. But if you pay attention to the overall trend, I mean, they are right on the mark. And this is a prediction that was cut in 2016 or so, when this plot was made. But right now we know the value here, and it is right on the spot, like there. So they are getting good at predicting what goes on, and they know the cause. The cause of this temperature rise is the increase in greenhouse gases that we are pumping into the atmosphere. There is no other thing. If you remove I mean, this is a model, you can play God, you can remove the CO2, and then you will not see this increase. So CO2. And so they have known this for many years already, so they can propose us the key to save ourselves of a very difficult, very dangerous time that we are facing if we keep on increasing the amount of CO2 in the atmosphere. Well, if you keep on doing that, we will reach very high increases in temperature. And if you reduce the amount of CO2 that we are pumping in, then we have a chance of not increasing much more than 2 degrees, 1 point something degrees regarding this pre-industrial level. That will be the dangerous part of this curve. So we can go back and see what are the sources of the greenhouse emissions. This is for the United States, this is for the rest of the world. So transportation and electricity make up a big piece of this pie. And I was going to show another slide, my last one, showing an interesting development. This is the pie of power generation for electricity in the United States. And it's made up of coal, a lot, natural gas. This has been increasing and this has been decreasing, but not a lot. And then these ones are the alternative or renewable sources. But look at what the Californians have done in the last few years. Their pie doesn't have any coal. They have a lot of renewables, some nuclear, a lot of hydro, and just this piece of a pie, which is less than half of burning fossil fuels. Natural gas is much friendlier than coal, but the plan of Californians is to keep on reducing this and increasing this part to reduce the contribution of greenhouse gases. They are not alone. Chile, for example, also has a large part of hydro, solar, and wind, and this part is increasing. This part is decreasing as time goes by. So this is the way to go. Reduce these parts of the pie, reduce the energy that we generate by coal or natural gas, reduce the standard cars that we use and use more electric cars or hybrid cars or hydrogen powered cars, whatever does not pump CO2 in the atmosphere, if we don't want to follow this path and get in big trouble in the future. So this is it. We should be paying more attention to science in order to save ourselves. It happened to us with coronavirus. He got us. If this global warming gets us, it's going to be much harder. So this is it. I will end here with this slide, which is a beautiful picture of the Earth and Moon system, not by NASA, by the Chinese microsatellite with some experiments on it that a couple of years ago flew and went around the moon. Thank you very much for your attention.
Thanks, Alejandro, for that excellent presentation. As a quick reminder to people, if you have any questions, please do submit those either through the Q&A in Zoom, or you can do it either via the chat window in YouTube or the Google form that I've just sent out to you. To give you an opportunity to do that, I have a couple of questions that have already come in, so we'll start with those. Looking back to some of the historical aspects, looking way back to obviously the ancient Greeks and things, how do we know some of the theories and ideas that have come from there, and how many, it sounds like a lot of the principles of them are still relevant today, even if they didn't necessarily get all of the details right compared to the knowledge we have, you know, in present times?
Well, how do we know? I mean, this during ages, I mean, millennia, the people that belonged into the institutions of study and learning, like the Alexandrian Library or similar ones that were around the world, devoted themselves to study manuscripts done by even earlier researchers, and they copied the manuscripts. Part of their work was to copy them, and they will copy and comment. So as time went on, you had copies of, I don't know, Aristotle or Plato with comments from someone else. And those things kept on moving a long time, probably with some small changes, no one knows. But, you know, they were writing in parchment or papyrus, early versions of paper. So the books or manuscripts will not last very long, just a few decades. So many things have been lost. Also, the manpower they had was not great. So at times, they will just find that some author was the, I don't know, best one, and will just copy it, him or her, and forget about some other ones that were before. So we did lose a lot of wisdom, or at least approaches to wisdom that used to be around, I don't know, 1,000 years ago or 1,500 years ago.
Understood. So it'll be, I think the other thing as well that's kind of come up in a couple of comments and questions is obviously a lot of the other historic civilizations that had quite a good understanding of how the universe sort of worked. There's a lot of Chinese sort of science that came out historically that's quite interesting to look at and compare to the sort of the Western world versions that we see about, and how that kind of compares. So it's just kind of an interesting idea of the sort of two different civilizations and studying the sort of same phenomena in the universe.
Yes, I mean, and there were very powerful cross-pollination between some of the wisdom from the, I don't know, the eastern part of the world, like the Arabic numbers, or that came actually from India, but the Arabs straddled between the western part and the eastern part, so they were the carriers of that knowledge. And I cannot imagine these ancient natural philosophies doing math without the numbers that we use now. I mean, it must have been really painful. But on the other hand, these civilizations did not get to the point of finding, at least, maybe they were finding the explanations to reality that the Western part of the world did. Historians have been going around that and looking for causes, but I mean, history goes just one way. Yeah. And this realization of the world, it was like that.
Understood. A couple of questions that have come up since we've been talking. So how do you think people came up with the idea of planet Earth sort of being flat? Why do you think there's been this sort of resurgence in it after, everyone at school is taught, our best knowledge from Newtonian physics? Where has this idea sort of come from, and why has it got sort of fame, I guess, if you want to call it, today?
Oh, you mean the present state of affairs regarding this? Yeah. I don't have the least idea. I mean, it started back in the 19th century, late 19th century, with a British guy that thought that there were some things that were, I don't know, consistent in astronomy. And he thought that the solution for that was the flat Earth. But I mean, I live in the southern part of the world. I mean, and I know that the southern part of the world, when you move between Australia and South America or South Africa or Antarctica, doesn't look at all like that. I mean, distances are not like they should be if you pay attention to the flat Earth map. I mean, there are thousands of geometrical arguments that you can make, but I don't want to enter in geometry because we are far more advanced than that. I mean, we will not be talking like this if we didn't have physics. And physics explains why the Earth is a self-gravitating body and ought to be approximately spherical.
Okay, so it's kind of linked to the previous question. So what strategies, or again, this is perhaps not strictly physics, but what strategies do you kind of recommend to get this message across about scientific literacy and the idea of things? And how do you, how do we encourage people to sort of critically look at things and sources, and how well seated it is in, I guess good science is not necessarily the right word, but you hopefully get the idea of
yes,
what's behind that.
You know, one thing that I rescue or I get from the people that is a believer, and I emphasize the believer character on the flat Earth, is that they don't take things for granted. They want to find themselves. And I think that that's a good start. I mean, and you have to have passion. It looks like many of them have a lot of passion put into this, but you need to mix that passion with some thinking. You need to learn, I mean, the things that, I mean, humanity has been learning painfully at times along many centuries. I mean, that those sorts of ideas do not make sense. And you can observe, I mean, there is a, what's the name? Al-Biruni, an astronomer and mathematician early on. He ended as a part of the court of the grandson of Genghis Khan in Samarkand. He was the founder of the Observatory of Samarkand, and he measured the roundness of Earth just going up a mountain and using an instrument that allowed him to check that the horizontal, I mean the line horizontal in your place, was above the horizon. So the horizon was below the horizontal. And you can do that today with the theodolite. I mean, this instrument that surveyors use to make maps. And you can climb up a high mountain and do that. And you will see that the Earth goes down. I mean, Al-Biruni did that in, I don't know, the 11th century or something like that. Well, so that is a part that I rescue. On the other hand, right now, I mean, one good thing about this way of communicating that we have, it is fast, it is cheap, it is effective, but it doesn't discriminate. So in the internet, you will find a mixture of things, good things, quality information, quality news, quality advice, and trash, junk, things that people that put things up, I don't know, fake news just because they're going to grab clicks. And out of the clicks, they get money. So we are like sitting ducks of these things. And we should pay attention to that because we are the target. As customers, we are the target. So when we see something that inspires us to go after it, because it is, I don't know, it piques our attention, we should get worried on internet, or at least we should get attention. We should pay attention. Look for good sources of information. There are many around them. Encyclopedia, web pages of universities. We should probably be doing more of that. I mean, researchers, astronomers, but it's not easy. I mean, there are so many things that we need to do, and I don't know.
I think that's a fair assessment of you should always look at the source of where you're getting your information from.
Yes.
So I think one sort of summary comment, and just to wrap up, is as a fellow scientist, I often think that science is always our best understanding of the universe today. And I think the history that you went through today kind of showed that it's an evolution of our knowledge. But a theory only becomes invalid when you get a measurement that doesn't match it. And when you have a measurement that doesn't match it and it is valid, you have to come up with a new theory that explains both the old theory's predictions as well as the new measurement that breaks it. So you can't just kind of be like, well, the old theory was wrong because we had this one data point. You sort of have to come up with a new theory that encompasses the two. And I think that's always important for people to keep in mind, is you can't just look at that one thing. You've got to look at the whole picture when you're kind of coming up with the current theories. So I think that's that's certainly how I try to convey it. I hope that sort of gives my perspective.
That's a nice, I cannot find the word, way of putting what I was trying to say. I mean, you cannot speak of the shape of the Earth alone, because there are many other things that go together with that. So you will need a whole new physics that explains not just that shape, but I don't know, even that, our teleconference.
Absolutely. So, well, thank you, Alejandro, again. The recording of tonight's talk will be available on YouTube later this evening. And if you're interested in that one, as well as our previous talks, you can find them on our YouTube channel, which is Our Universe Revealed. We are back next week at the same time, Tuesday, the 12th of May. And that is a talk by Dr. Erica Holmbeck, who's a recent graduate of the physics department at Notre Dame. That's at 7 p.m. the same time. She's going to be telling us about her cutting edge research, and in particular, how we're able to create the elements you and I are made of. Perhaps more importantly for a lot of you out there, those precious metals, that gold and heavy elements. So think of it in a way that's more as where alchemists try to turn metal into gold and failed. The universe has succeeded. So I hope you'll join us same time, 7 o'clock next Tuesday for that talk. In the meantime, thanks to Alejandro again for his presentation. And thank you all very much for joining us. Stay safe out there and hopefully see you back online next week. Bye-bye for now.